Hello students. Today we are going to talk about a new topic which is thermodynamics of open systems. And here I'm going to introduce you to the concept of what is known as a chemical potential. So chemical potential is a quantity which is classified as an intensive thermodynamic variable. Now, what are the different types of equilibria that we have come across? We know that a system, when I'm describing its equilibrium state, it may be in thermal equilibrium or it may be in a mechanical equilibrium or it may be in a material equilibrium depending on how the system is interacting with its reservoir. And therefore, we have already seen that these three types of equilibria depend very much upon the wall that separates the system and the reservoir. So in the discussion that follows, I shall assume that this wall surrounding the given system and the given reservoir, this wall is an adiabatic, rigid and impermeable wall. And therefore, the given system and the given reservoir together form an isolated setup. So this is a very simple representation of the fact that I am saying that the universe is isolated. And system is a part of the universe that I am interested in, and reservoir is the rest of the universe. Now, in connection to this kind of situation, I talk about the thermal equilibrium between system and reservoir, whereby I talk in terms of the intensive thermodynamic variable temperature. Now, when I talk about a mechanical equilibrium between the system and the reservoir, then what is the intensive thermodynamic variable that I talk about? Yes, we talk about pressure. And when I am talking about material equilibrium or equilibrium with respect to transfer of matter from one region to the other in this setup, then I will be talking in terms of a new thermodynamic variable, which is chemical potential. So let us now see the kind of concept which leads to the introduction of chemical potential mu in the literature of thermodynamics. So first of all, this is what we have already seen for a thermal equilibrium. So now this isolated setup of system plus reservoir, they are separated by a diathermal wall, and I maintain a temperature difference between the system and the reservoir. So in this situation, I have the system at high temperature and the reservoir at low temperature. As a consequence, there will be energy flow from the system to the reservoir in this direction, where energy will flow in the form of heat introduced by the difference in temperature between the system and the reservoir. Now consider the other situation. If I had the system at low temperature and the reservoir at high temperature, and if there was a wall between them which is rigid, diathermal and impermeable, what is going to be exchanged between the system and the reservoir? Of course, heat will be exchanged between the system and the reservoir and the system, whereby the energy in the form of heat will flow in the direction leading to the from the region of high temperature to the region of low temperature. Then the question is, what would be the final equilibrium state when we allow the flow of energy between the system and the reservoir either in this direction or in this direction? The answer is when the system and the reservoir have acquired equal temperatures all throughout this setup, then I would say a thermal equilibrium has been established between the system and the reservoir. Therefore, in terms of reservoir properties, equal temperatures or equality of a relevant intensive variable decides the condition of equilibrium. Similarly, when I separate my system and the reservoir by a movable wall, in that case, if volume is the only quantity that is being exchanged between the system and the reservoir, then I would understand that the direction of spontaneous exchange of volume would occur from a region of high pressure to a region of low pressure. So if I maintain the system at high pressure, the volume will be exchanged in this direction. If I maintain the reservoir at high pressure, then the volume would be exchanged in this direction. So, what is the condition of mechanical equilibrium between the system and the reservoir? This is given in terms of equal pressure between the system and the reservoir. So, if the pressure pushing the movable wall from this side is equal to the pressure pushing the movable wall from that side, I must be attaining mechanical equilibrium between the system and the reservoir. Now, I'm going to generalize these concepts into the material equilibrium, where I'm thinking about equilibrium with respect to matter flow. Now, here is a typical experimental setup where I'm going to look at matter flow. So, what do I have here? Here, I have the system and the reservoir as in combination as an isolated setup. But I have a separating wall which is porous and diathermal. Therefore, what are the quantities that can be exchanged between the system and the reservoir here? First, you can have exchange of energy as heat, and you can also have matter flow. Now, I understand already that the direction of flow of energy as heat will take place from a region of high temperature to the low temperature. Now, can I say something about the direction of matter flow? And for this purpose, I'm going to require an intensive variable. So let me define this intensive variable as the chemical potential mu. So this is a perfectly general condition. So what I will say is, well, the equilibrium with respect to matter flow will be established when, first of all, there is equal temperature between the system and the reservoir, and there is a equal chemical potential between the system and the reservoir. And as a result, if you make measurements at the wall, you will find that there is no net flow of matter across the wall, and both the system and the reservoir is having now equal temperatures. Of course, you could have induced a transfer of matter from the reservoir to the system if you allowed the reservoir to be maintained at a higher chemical potential. Then matter would flow from the reservoir in the direction of the system. Now then the question is, how do I define this chemical potential? So it is a quantity that we have introduced to mimic the role of temperature and pressure, but with respect to a process when there is a matter flow. So now I will start the discussion of formulating the thermodynamics in such an open system where the system and the reservoir is separated by a wall that is porous and diathermal. So in that case, the system and the reservoir can exchange both energy and matter. And I would describe the equilibrium state of such a setup of the system in terms of a diathermal, rigid and permeable wall, such that the equilibrium state of the system will be specified by specifying the temperature T, volume V and the chemical potential mu. Now let me consider another situation where in addition to the energy and matter, I am allowing exchange of volume between the system and the reservoir. So once again, this is an example of an open system whereby now my wall, in addition to being diathermal and permeable, is flexible as well. Therefore, how are you going to describe the equilibrium state of the system under such condition? We are going to specify the equilibrium state by mentioning the given temperature value that I can measure using a thermometer, the pressure of the reservoir that I can measure using a barostat, and finally, since the equilibrium state has been achieved with respect to matter flow, I would say that this setup will have, this system will have a given value of the chemical potential mu. So this basically tells me that yes, so what we are doing is we are simply generalizing the way we were looking at closed and isolated systems and the way we were defining the equilibrium state when we were varying the nature of the wall and hence the way the system interacts with its reservoir. Now, when I move over, then let us start with the general definition of chemical potential. So, chemical potential mu I is the rate of change of the thermodynamic potential with respect to change in number of particles. Okay, Ni of the type I. So in general, let us say that I have capital M different types of particles in my system. So of type 1, there are N1 particles. Of type 2, I have N2 particles, and so on and so forth. In that case, mu I gives me the slope of a plot of thermodynamic potential with respect to the change in each of this type of number of particles, where I can be going from can go from 1 to m. Now let us look at the thermodynamic potential U. In this case, by the definition, I know that du is equal to TdS minus PdV for a closed system, where dNi was equal to 0. Now, by definition, for an open system, I can write du is equal to TdS minus PdV as before, where I have added an extra term which involves a summation over the contributions of all types of particles present in the system, and therefore the summation runs from I equal to 1 to m. And what is it that I am summing over? The summand now involves dni, that is the differential change in the number of particles ni during the change in state, which results in a change in the value of the internal energy by an amount du. Once again, please remember, du is still of the form m dx plus n dy plus q dz. Therefore, I understand that the variation of du now depends on ds, dv and dn. And what I find is, by the definition of the exact differential, what should be mu I? Mu I must be del u, del ni, keeping all other variables constant. Now, what are the different variables that we would use for a situation where the thermodynamic potential is u? The different variables that we use are S, V, then N1, N2 and so on up to Nm. So when I am talking about mu I, then I have to keep all j's not equal to I constant when I define mu I. So that is exactly what I have written here. I'm keeping S constant, I'm keeping V constant, and then I'm keeping all values Nj, where j is not equal to I, constant. Now, think about the situation where I can define chemical potential with respect to the enthalpy. So, when do I use enthalpy as the thermodynamic potential? That is when the equilibrium state of the system is defined in terms of Sp, N1, N2, etc. up to Nm. If that is so, then I would say that changes in the values of Sp and the Nis will give me a corresponding change in the enthalpy value. So for the change S to S plus ds, P to P plus dP and Ni to Ni plus Ni, what would be the corresponding change in H? That corresponding change is going to depend on ds, dP and dni. So the prefactor of ds is T because del H, del S, Pn is T. Similarly, I have V here. Then what is going to be the chemical potential under such condition? The chemical potential is given by del H, del Ni. Now I keep S, P and all Nj is not equal to I constant. Similarly, I can define mu I with respect to the rate of change of the Helmholtz free energy as well as the rate of change of Gibbs free energy. So, to remind you once again, when shall I use the definition of mu I as del G del Ni Tp, keeping temperature and pressure constant, and all other Nj's where J is not equal to I constant? If I have an equilibrium state defined by temperature, pressure and the values of all possible values of Ni's, and I have now carried out a change in state that gives me a new equilibrium state as T plus dt, P plus dP, and each Ni now has changed from Ni to dNi. Ni. Now, during this change in state, you would understand that G will go from G to D plus dG. And my question is, what is dG? So if I go back and look at this expression, dG will depend on dt, dp and dni. And therefore, I can say here, by the definition of an exact differential, mu I is going to be del G del Ni, keeping temperature, pressure and the number of all other types of particles in J, where J is not equal to I, constant. And what we are going to see next is that this is the most commonly used form of chemical potential. Therefore, in the literature of thermodynamics, you will find that chemical potential is most commonly defined as the partial derivative of Gibbs free energy with respect to change in the number of particles of the ith species present in the medium. And you then write dG is equal to minus SdT plus VdP plus mu I dNi. So this basically banks on the fact that in many real applications, we are actually looking at the properties of the system at a given temperature, pressure and number of particles. So I define the equilibrium state in most commonly encountered experimental systems at a given temperature, pressure and the number of particles of each type of species present in the system. And what is the thermodynamic potential under such condition? You already know that the thermodynamic potential under such condition is the Gibbs free energy, and therefore under such condition that I use the chemical potential as the partial derivative of G with respect to Ni, keeping all other variables T, P and Nj's constant. Now with this background in mind, let us go ahead and think of how to define the chemical potential for a pure substance. Now when I'm talking about a pure substance, how many different types of particles is present in it? So the number of components is going to be equal to 1. So I'm going to focus first on the specific case where capital M is equal to 1. Now, a pictorial representation of a system would be something like this. Remember, this is what we had used to describe an isolated system, where the system containing these particles, these green particles, make up the pure substance that I am talking about, and the system is separated from the reservoir by an adiabatic, rigid, impermeable wall. Now, if I am talking about a pure substance, a system made up of a pure substance that is in contact with a thermal reservoir and a particle reservoir, then by the definition that I have introduced, I am going to define the equilibrium state by specifying the temperature, volume and the chemical potential mu. Now this is going to be a typical picture of an equilibrium state that I'm talking about. Now the system is surrounded by a diathermal permeable wall which is also rigid. Therefore, at equilibrium, the volume of the system, which is the volume of this white box that I have here, that is going to be of my concern, and that remains constant at V. But now since the wall is permeable, therefore the green particles from inside this system can move from inside the system to the reservoir. and it can also come in. And therefore, all I'm saying here is that at equilibrium, this system will have the system, that is the white box that I show here, that will have a given value of temperature, given value of volume, and a given value of the chemical potential. Now, when I have such a situation, let me say that n is the number of particles present for this pure substance. Then very easily I can generalize this expression and write down that G is now a function of Tpn. Therefore, dGTpn is going to be a function of dt, dp and n. And what are going to be the coefficients appearing with dt, dp and dn? So this is going to be minus s, this is v, and this by definition is mu, where mu is the chemical potential of the pure substance that makes up my system. Now, if I look at this expression, I know that mu is del G del N Tp by definition. Now, I look at this, the right hand side of this, and that is where I get the definition of mu. Now, this has to be equal to the molar Gibbs free energy. Now, Gm here is defined as the molar Gibbs free energy at that given temperature and pressure. Therefore, for 1 mole of the pure substance, I have dGm, that is equal to minus molar entropy into dt plus molar volume into dp. I can put it back to the value that I have got here, and I can very easily write down that d mu must be equal to minus Sm dt plus Vm dp. Now, in this entire discussion, what is the property of Gibbs free energy that we are discussing here? I note that Gibbs free energy, an energy function, is an extensive property. Therefore, I can always write down G at a given temperature